Thank you. Yeah, good afternoon, everyone. My name is as introduced. I'm from the University of Agriculture Makurdi, now known as Joseph Sarwuan Tarka University. And in our research group, we partner with University Science Malaysia to do some works on photoelectrochemical water splitting. In this work, I am presenting a work on the photocatalytic properties of molybdenum oxide photoelectrode synthesized by spray pyrolysis method. Fossil fuel deposit is depleting, and there is alarming increase in environmental pollution due to increase in the world population and industrialization. And this calls for the search for alternative energy sources, which are clean or green, that can reduce environmental pollution and that can replace fossil fuels. Like in Nigeria currently, there is high increase in fuel pump prices. So there is need to search for alternative energy sources. And photoelectrochemical water splitting is a technology that utilizes solar energy to drive catalytic water splitting reactions to produce hydrogen fuel gas and the oxygen gas. And the mass production of hydrogen fuel is challenging due to the low efficiency of photocatalysts. And there is many methods have been devised to improve the efficiency of photocatalysts for water splitting, such as doping of matrix element compounds, such as composite formation to create heterojunctions that can enhance charge separation and transport. And also different synthesis routes have also been applied, which have shown to influence the output or the efficiency of the photochemical reactions. And the molybdenum oxide is a semiconductor that has a suitable band age alignment that can support water splitting reactions, although it suffers from low efficiency due to its large band gap. Therefore, doping methods have been used, composite methods have been used, and yet we can still try other synthesis techniques that might produce molybdenum oxide films that with different morphologies and the optical and structural properties that can enhance water splitting reactions. And it is surprising to know that molybdenum oxide has rarely been prepared by the spray pyrolysis method and deployed for photoelectrochemical water splitting. Search in the literature shows that such report is scarce. Therefore, in this work, we try to investigate the water splitting properties of molybdenum oxide prepared by spray pyrolysis method, and it was tested in a 1 molar potassium hydroxide solution. Materials and methods. We prepared a 0.05 molar solution of molybdenum oxide using molybdenum oxide powder, which was dissolved in a 3:1 volume ratio of hydrogen peroxide and deionized water. And figure 1 here shows the schematic of the spray pyrolysis system. And the substrate was placed at a distance of 35 centimeters away from the spray nozzle to receive the spray mist. And the photoelectrochemical cell takes the form in figure 2, where it is a 3-electrode cell, which comprises of the photoactive molybdenum oxide film, which acts as a photo anode, and the platinum wire, which acts as the cathode. And then we use the silver chloride reference electrode. And the band age alignments of molybdenum oxide are shown, which is in the scale in the vacuum scale, which shows that it is the conduction band is above the hydrogen production or reduction reaction, and then the valence band age position is way above the is well above below the oxidation reaction. Figure 3 here shows the surface morphology. Figure 3A shows the surface morphology. We can see nano aggregate, which was measured to be 916.7 nanometer. And then the crystal structure was measured by XRD diffraction method, which is figure C. And we can see that only one phase of molybdenum has been produced, the alpha phase. Which is the most stable phase of molybdenum oxide that is chemically and thermally stable to undergo water splitting reaction without being degraded. Structural parameters were investigated at the highest peak of 210, and we can see that the crystal size of about 141.27, and the density, the dislocation density, the microstrain, and the deposition faults are so high, which shows that there is high defect in the material, in the crystal structure, due to during the deposition process, because the parameters are very high. The density, the dislocation density, the microstrain, and the stacking faults are so high, indicating that there is high crystal defects that were formed during the film deposition. Eventually, could be due to the high surface temperature, which is about 400 degrees Celsius. And figure 4 shows the optical reflectance measurement done by UVV's near-infrared spectrophotometer. The band gap was estimated to be 3.2, which falls within the band gap range of alpha phase molybdenum oxide. And then photoelectrochemical measurement in using this photoelectrode in 1 molar potassium hydroxide shows that in the dark, the photocurrent was so low, below 200 microampere at a bias of 1.2 volt versus silver chloride. Upon light illumination using xenon lamp, UV light, the photocurrent was observed to increase significantly up to a high value of close to 1,000 microampere centimeter square. And then for easy comparison, we converted the response to reduce reversible hydrogen electrode, so that it can be easy to compare with other data. And as shown in figure 5B, to check the stability or to check the linear sweep voltammograms gives us information about the efficiency of a photoelectrode during operation. Now, to check the charge carrier separation and transport process and the stability of photoelectrode, one needs to conduct the chronoamperometry measurement, which is the transient photo response. Now, we can see in figure C that a good stability can be observed, which indicates that the photoelectrode is chemically stable. Although we can see high dark current, which is above 100 microampere, that is when light is switched off, which is an indication of high crystal defect, which is agreeing with the XRD analysis that has shown high values of dislocation density, microstrain, and stacking fault. And then in order to understand the impedance or the resistance during measurement that is responsible for the performance of the device, we carried out electrochemical impedance measurement at 1 volt in the dark. And to obtain the values, we had to use a simulated circuit, which is shown in the inset of figure 6A. And it can be observed that the charge transfer, the charge recombination reactance was found to be about 141.7 ohm. This value is quite high, and which actually supports the reasonable photocurrent density observed in the voltammograms. And the average electron lifetime was calculated from the Bode plot, which is on figure 6b. And the electron lifetime was found to be 0.26. This value is also quite low, which shows we support quite a reasonable performance of the device in terms of the output photocurrent density. Now, based on this performance, we can see that the spray pyrolysis method is quite a promising method for preparing photoactive molybdenum oxide film that can be used for photoelectrochemical water splitting. If the synthesis parameters are improved, it is hoped that the performance will increase. And it should be noted that the photocurrent density has a close relationship with the hydrogen, with the actual hydrogen volume, that hydrogen gas volume that can be obtained from a photoelectrochemical cell. So it is hoped that this research will open ways and open doors and stimulate research interest in preparing molybdenum oxide photoelectrode by using the spray pyrolysis method. Thank you for listening.